Hey, welcome back to the book club. So we're on Rocket Propulsion Elements. This is a great book on liquid rocket engines. Sorry, all rocket engines. This happens to be the one that I learned a lot of stuff on liquid rocket engines on. And today we're going to get into thrust chambers and that liquid combustion. And so one of the cool things, I showed this last time, but this is a great sort of schematic of what's happening inside of a rocket engine. And then we're going to kind of start at the top with the injectors and then kind of work our way through the combustion chamber and then also the regen cooling and things like that. And we'll come back sort of after that as well and get into more of the details of the liquid combustion. But ultimately, the rocket engine is combining the injectors to have both a aux source, so I'll sort of use this aux, a little box, and then a fuel source, right? And hopefully these show up in multicolors. I'll try to stay consistent on the color scheme as we go today. And so if the fuel comes and meets the aux, that would be just called a doublet. So this is a standard doublet. In fact, I'll see if my blue will work. Okay, so that's just a doublet. And ultimately, you would have a whole array of these, right? So you see in this picture here, there's a whole array of them. And so you would sort of continue that along, but you basically have one fuel hole hitting one aux hole. That's not a ton of what we have normally. Okay, there's another one that's called shower head, and it's basically straight. And so that's where you have your aux, there's your color fuel, and kind of shooting out. And a lot of times what they'll do with shower heads is they'll sort of impose a swirl on there, okay? And so these are going to shoot straight, they're going to kind of coaxial and swirl and then sort of mix that way, as opposed to sort of a direct impingement like you have here. Okay? There are some rocket engines that, in fact, on the X-15 they had this where you sort of have a pre-mixed area, and so I'll draw that like this. Actually, I'll draw in blue. So pre-mix, and where you basically have them coming in, and then you basically fuel and aux coming in, mixing, but not combusting and then shooting into the chamber. You don't see that as much. The ones I think I see on the X-15 was actually sort of a rocket engine side of a rocket engine, and that was more for instability, which we'll talk about. So you don't see that one a ton. And then you kind of keep going down that you can think of doublet and then triplet. This is starting to get a little more common. Now, a little harder to make. So this one will have to be pretty careful. Aux, I'll do a couple rows of these so you can see what's going on. And then fuel. That'll be enough. And basically, each fuel usually different configurations, but on this one I'm going to have the fuel go straight, and then the aux is always going to sort of pair off in two different directions. And so what's cool here is that you end up creating your combustion impingement here, and so you're not sort of imbalanced. It's symmetric because your oxidizer and your fuel is going to have different densities, and that way it's going to have different momentum when it hits. And so like this one may yes, it'll impinge, but it may come off at an angle, where this one you're sort of guaranteed to be straight. Okay, and then there's one called a splash plate. And that one, I'll just draw kind of a couple of these. There's a fuel. And so you may think of this kind of going two directions. This coming here, there's aux. And then there's actually, you have that then hitting a plate and then kind of going through. And so you get the impingement, but then the extra mixing. And so that one's pretty interesting too. Now, all of these, really the trade-off is what you're trying to do is get your best amount of mixing. But you're also, I started to drew these as boxes, but really you have to think of each of this as sort of machined into some sort of surface. And that's what you're seeing here, right? Where the fuel is actually coming in from the side, and then the fuel holes will be shorter, and then the aux is coming in from higher up, and so the aux injectors are actually going to go further up. And so there's a lot of machining that gets involved in this. And this is not, this injector face is not regen cooled. And so while the liner of the combustion, we can use usually fuel to cool it, and then the fuel enters here and then goes in. The liner is uncooled. And so basically the cooling that happens is by the standoff. So you kind of push your standoff to a point, hopefully back in here we have is sort of either aux or fuel, but not really a massive combination of the two. And it sort of kind of pushes the start of combustion a little further away, and that helps keep this cold. Now, you also have fuel and aux running through the surface, and so that does help keep it cool as well. But a lot of things people tweak and work on. And you're going to see this a lot, but CFD is getting more powerful and more powerful, but still, this is a really hard problem from a CFD point of view. So it's not that helpful. It really doesn't nail the physics unless you do a really crazy supercomputing version. Even then, it can be challenging. And so even experimentally, this is really hard to do because of the temperatures and things like that. So a lot of this actually just comes from, if you go back to what we did in the past, in the 1950s, 1960s, you sort of try and experiment. And so that's really what happens a lot. And a lot of times in engine development programs, one of the largest time and then cost is actually trying to get your performance up by tweaking the parameters you can, like mixing and swirl and things like that, momentum ratios, and then avoiding combustion instabilities. We'll talk about those. And for both your performance and avoid your combustion instabilities, you don't have that many options to go attack. Okay. Now, a very common one that is not sort of these holes is actually called a Pintle design. And I'll draw that in blue. And so if here's a rocket engine, okay, go. The Pintle actually comes through the center. And I'm not trying to draw this to scale. I'm trying to show a little more obvious. But the Pintle is usually a whole bunch of holes here, radially. And I'm not sure that's coming out. But what's going to happen is the aux is going to come out of these holes radially. And then the fuel is going to open up here usually and come down the center pipe as a liquid sheet. And so you end up having that sort of sheet of fuel into a radial spray of aux. Now this is a very classic design. SpaceX Raptor, not Raptor, Merlin engines, the Virgin Orbit ones were done. This is all that design. And you can adjust the length and things like that. But what's really cool is you end up getting some kind of recirculation back in here that sort of helps. So it actually helps cool. It also extends mixing. And one of the criteria that sort of is important is usually this length. So that is the generic length, but what's it called? A combustion length, L star. All right. And that's usually the volume of the combustor divided by the area of the throat. So this being the area of the throat. That's the combustion length needed to sort of fully combust this. Now the experiments that are run are sort of fully pre-mixed, and then they kind of run it, and then you get these experimental values of L star. So the Pintle actually reduces this length, of the rocket engine is less than the length of L star, but your effective L star from a combustion efficiency is up. So a lot of times these rocket engines end up being shorter, as opposed to ones like this. And this is not scale, but ones like this that are just sort of shower head or injector head need to be a little bit longer. Yeah, so it's a trade. It's a trade. And I'll show you some pictures here. This is the Space Shuttle main injector. And so you can see, again, these really long surfaces kind of going from the aux manifold here, the fuel manifold here. And so the fuel one's kind of, you can see the little short one here, that's the fuel, whereas the long one here is tapping up into that aux manifold. So that's pretty cool. And then this is a picture from the Apollo F1 injectors. So again, you can see all this machining and things like that we did back in the 50s and 60s. Pretty impressive. Now, these big sort of pieces here, those are called baffles. And what you're doing there, that's for these acoustic instability modes that can pop up. If you just have a regular rocket engine, the modes that you can create are sort of the rocket engine size, and then sort of half the rocket engine size, quarter of the rocket engine size, things like that. And it's in a circular disk, so modes I say generically, but for your mathematicians out there, this would be more like Bessel functions or things like that. And then you can get these modes, and you can get azimuthal modes as well that sort of start going. And so, in order to sort of suppress those modes, you have these sort of barriers right next to the injector, so that as this is mixing, it doesn't, it sort of suppresses that one mode. So this is a lot of what you end up doing. Again, sometimes kind of trying to error. There are other times where you could sort of estimate the instabilities and sort of know that going in, you might have to do something like this. Okay. And then coming back here, let me come back to the diagram. Important one as well is stiffness. So while I've sort of drawn a picture here, the manifold, and so if you follow the aux up here, I'll just sort of draw a box. Oh, you can't see that. Shoot. Here, that's aux. Okay, there you go. And then let me just sort of draw a box over here. It's fuel. Not to scale or actually you do. It's like you see them here. So there's the fuel manifold. Here's the aux manifold. The pressure drop to go across that. So the delta P over the pressure of the combustor. Okay, this is called stiffness. And what we have found in the rocket engine world is that you need this to be at least usually 30%. It's a common number around there. So it's not a hard number, but you need about a 30% drop from your manifold here into the combustion chamber in order to sort of keep pushing and prevent any instabilities coming up. Now, as I've covered in other videos with Venus in a rotating detonation engine, that's actually one of the challenges. Is detonation usually requires more, especially if you're gaseous. Although we've been able to bring it down quite a lot, being liquid detonation. And so that drives a lot, because that stiffness then drives your pump size. And then, as we talked about last time, all these different cycles, the way you power your pumps is actually by stealing a little bit of fuel and oxidizer. And depending on your cycle, there's ISP costs that can be greater, but also complexity. Okay, so that's a big one. And then sort of leave this picture here. So that's from a design point of view. Leave this picture here. Normally, the fuel, we'll come back to here, the engine is cooled by the fuel. And so before it enters the manifold here, I'll actually come back to the pump, usually the fuel will come in. I'll draw it sort of here at the midpoint of the nozzle, and then the fuel is going to run all along the inside, and then it's going to enter the manifold, and then it's going to come in. Shoot, that was a wrong color. Okay, apologies. Fuel is green. Okay, the fuel runs along there, and then it comes in. Okay, they usually cool the fuel because cooling with an oxidizer, whether it's oxygen or something else, is usually scary. Because if you start getting it burned through, it's an oxidizer, it'll just kind of keep burning through. Now at Venus, we actually are cooling with the aux. We've taken over that challenge, mainly because we wanted to keep the fuel as jet fuel. So RP1 is just kerosene with a good filter. Jet fuel is the same stuff, but it has all these other aromatics that when you use jet fuel or some sort of impure kerosene, and here those aromatics are not stuff that's not kerosene. Those aromatics are actually going to gunk up and form a waxy substance, which is going to clog your range of cooling holes. And by the way, these are like really, really tiny. So 3D printing's really helped a lot in terms of being able to manufacture this in a very unique way. You can imagine what happens here. So in fact, the normal way that you manufacture sort of classically is this would be copper, which you would then machine. You would slot all of the holes. You would then pack the holes with, the channels. You would pack the channels with wax, and then you would grow nickel on the outside. So the Space Shuttle main engine here actually took about 3 years, if I remember correctly, to grow the nickel on there. It was a really long process. I know Virgin Orbit, it took us, I think 6 months, something like that, to grow enough nickel to where you would come back and machine it. So the nickel is what's providing the strength, and you literally are an electric bath. You're adding the nickel sort of atom by atom with a bath and a voltage. So that's why 3D printing is really changing. This is one avenue where 3D printing is changing the rocket industry quite a bit, because you could print this. Now the inside surfaces are not going to be as smooth as sort of the classical way, but if you can handle the sort of the roughness of the print, it works out well. That's what we do here at Venus. We print our regen engines for detonation. So it's quite a lot. Now I left it intentionally here on the nozzle. If you're in a vacuum space, this nozzle will continue, right? We talked about that last time. So usually you cool your nozzle out to some point, and then after that, it's actually enough to be radiation cooled, because the exhaust here is getting faster, but it's also getting colder as you're sort of trading heat for velocity. And so that's sort of, you see that here in this picture where you can see the fuel coming in. The fuel is going to then go up. You may have an attachment point here where you would put a nozzle past that. All right. And then I've talked about this a couple of different times. So regen cooling, this is just using the fuel. And so honestly, the biggest heat flux is actually right here. This is the gnarliest heat flux right here in the throat, where and the book kind of covers this a lot, and a couple good diagrams here. But this is usually the one that drives your entire regen cooling. Now you can have failures. Don't get me wrong, you can have failures throughout the engine, but that's the one that usually drives and sizes your regen. And so it's just convective heat transfer. So you're gonna solve for the velocities and densities and the Reynolds number and the Prandtl number and you know, all those analytical things to close it out, and then try it and iterate. Lots of iterate. So now one way you can improve that, it's called thermal barrier coating. And so I know I'll use green. I'm breaking my code here. But thermal barrier coating is actually a sort of a spray process you can spray onto your engine on the inside, and it's a ceramic. And ultimately, that'll help sort of drop that temperature. So you can think through. I'll draw it here. If you think through sort of the inside of the engine, so I'll just say this is versus radius. This is 0. You have here your sort of combustion temperature. This is the hottest it's going to be out at some point. Now here's where your chamber starts. And if you have a thermal barrier coating, you can actually drop this a little bit. But you're going to have convective cooling to this point, and then you'll have sort of, you know, if you have thermal barrier coating, maybe you don't have a huge temperature drop, but you have a massive heat flux drop, and then you'll have a drop thermally to your cooling channels. And so here's where your channel is, and this is where you then have that kind of cold fluid, and then you know, convection, and then out. So really the whole thing, the heat flux is equal to heat flux is equal to heat flux. So it's actually this full balance between the combustion chamber, the sort of the sum of the resistivities and heat fluxes of conduction as well as the convection on the backside, and then, you know, whatever you have out here, radiating out to space, or you know, it's usually constrained is radiating out of space at the very end. Okay, so that's sort of the basics of thrust chambers, and then when we get into sort of liquid combustion, I'm going to leave this off. I'm going to kind of draw here. Liquid combustion. And I'll draw this in green now to just kind of pop out a little bit better. So here's the chamber. I'm going to make it long just to give myself enough room. Okay. And there's some good diagrams of this in the book. You can look around the internet. I didn't see a great one on the internet that you know, otherwise I would have thrown it up here. And so ultimately, again, you know, we have sort of our injector surfaces. How are we doing? So this is your injectors. Okay. And then honestly, at this point, you are then sort of, I'll do ... This is atomization. I'll draw it sideways. So atomization, where you are busting these liquid streams into droplets. Okay. And then from atomization, you have vaporization. And honestly, it's the vapor that actually starts the combustion process. Okay. And so basically, once you have vapor, then it's going to go through. And I'll just sort of draw these orange circles, kind of like they do in the book. But this is then rapid combustion. And what's going to happen, you have these fuels that are at their liquid densities, and they're pretty quickly going to react in their vapor form and then get to their sort of very hot, you know, hot temperature density. So this is, you know, rapid combustion. But then we see after this is sort of this long, really, really fast process. And usually this is called the kind of stream tube. Stream tube, but it's still subsonic, okay? At least unless it's a detonation engine like Venus, unless it's subsonic. So you still have some combustion here, but the important one here is that V perpendicular is much less than V parallel. So will you get a little bit of motion, sort of, you know, perpendicular to these lines? It's not a ton. So there's still a little bit of mixing. But ultimately, you know, once you kind of start here, that's why all of your mixing really needs to happen back here, because if you're gonna if you don't have a ton of mixing, you're gonna end up having basically stuck. So there may be some little spots in here that are not well mixed. So it might be fuel rich or might be ox rich. Kind of back to we talked about last time. If I draw a diagram here of actually I'll stick it here. I think I've got enough room. So if you have ISP, so your performance versus your aux to fuel ratio, there might be some magical one here. I'll draw it as a curve like that. There might be a magical one here. If you can get it fully mixed, that's what you're trying to do, you get your best performance. What you end up having here, if you don't have full mixture, is that you have some parts of the engine that are operating in this condition and some that are operating in this condition, or you can get an example. And so without good mixing, you sort of get locked in these stream tubes. You're going to have either that fuel-rich zone or the aux-rich zone kind of going through. And then, of course, it'll come out and combust. And a lot of times, yes, in the plume, you still have some combustion. So especially with LOX RP, or honestly almost any kind of hydrocarbon, if you can continue to see that orange flame, really the orange is sort of the unburnt hydrocarbons that are sticking around. One of the measures of success, if you are using sort of a kerosene-based thing, is if you start seeing blue flame, then you actually are at that point where you're starting to really drive out all of those unburnt hydrocarbons. So it's sort of a great example of, hey, this is working well. And so that's actually where we're at with Venus right now. It's January of 25. And with Venus, we are slowly approaching sort of what you consider 100% of maximal performance with our detonation engine, but it's still looking orange. And so I actually see that as a positive. Like we're basically already we're about to cross over this long awaited for better than normal combustion. But I look at the plume and I say, oh, we still can mix better and even get more combustion performance. So it's exciting time. Detonation engines really change everything. Okay, so those are kind of the basics. Of course, then you have the throat, and then you got the expansion to supersonic that we've covered before. Now, the instabilities that you're really worried about, and I'll switch to green here for the sort of remainder for these instabilities. There's sort of broad categories of instabilities, and they're just by frequency, and the names are sort of self-descriptive. Okay, so this is a list of instabilities. And they're all acoustic instabilities. Honestly, is where it shows up. By acoustic is because you can detect the pressure, and honestly, as engineers, you can hear it. And so the first one is chugging. Okay, and chugging. I'll see if the orange starts chugging. This is usually 10 to 40 hertz, which we hear as a low frequency. Again, human ear, bass notes would be 40 is pretty low on the piano. Okay. If it's even on the piano, it may be right at that edge. So this is that pretty low that you almost feel more than you hear, from a human point of view. At some point, the frequency spectrum here is wider than our ears, so we don't hear it, but you just feel it. And then the next one, and usually this comes from the feed system. Usually this is a feed system issue, where you have some sort of combination of your feed system. Sometimes actually with the rocket. That can be pretty destructive. Okay. Next category is called buzzing. And that is usually around 400 to 1 hertz to 1 kilohertz. And this is usually you're usually injector issues. Okay. That's usually what's happening there. Okay, and it's not just injectors. Sometimes it can be eddies that are sort of trapped. So especially if you have, say, a Pintle, there may be a specific eddy that's actually eating your lunch on this one. Okay, so that's called buzzing. And then screeching. Again, I love these. Screeching is usually anything sort of greater than 1 kilohertz. This is now, as you can imagine, with the word screeching, this is starting to get into the higher frequencies for us as a human. And this is for sure, not for sure, but usually this is pressure waves in the combustor. And so that would be where some of those baffle plates I was showing you earlier would need to come in. That's what you're trying to sort of establish there. And then popping is not a frequency-based one, okay? But popping is sort of some sort of event that's happening. It's high amplitude disturbance is how it's described. Okay, high amplitude disturbance. And so it's not disturbance. Boy, that's horrible. Disturbance. Okay, it's not It's not a continuous thing. It's sort of something's happening here and there. So again, this is a dynamical system. So if you think of it as a dynamical system, it's sort of getting kicked out and then settling back in, or it's kicked out. It can be these weird modes. Maybe it's an eddy that you can't quite see, but it's some sort of event that is happening not continually, where we would describe it with one of these lovely words, but it's sort of happening here and there. That's not great. So that's called popping. Now, other modes that you can talk about, hard start is actually where you transition to detonation inside the chamber. That's usually destructive, unless you're making a detonation engine like we are. Okay, but hard start, a lot of times it can happen if you for some reason sort of leaked fuel into your engine. So imagine this is on an engine test stand horizontally. Okay, that's one of the dangers of doing it horizontally. I was talking about the benefits. And we'll talk about test stands, of course, later in the book, but if you're testing horizontally and you have some sort of leak, you're actually going to get it pooling up here, and then when you go start the engine, you've got pooled propellants, and it can go kaboom, right? It's just not what you're handling. And so there's value to testing vertically. Now, testing vertically is then a lot larger of a structure, so it can be more complex, more expensive, and things like that. So pros and cons to each. And then some people do in the middle, where they sort of test at 45 degrees. And that's honestly, that testing, that angle is set such that, imagine rotating this, where you're very sure that you're not going to pool propellants that's going to fully drain. Okay, so those are some of the basics, of thrust chambers and injectors. And of course, we'll dig in more to the testing later on in the end of the book. So again, if you're liking this, please like and subscribe, and ask any questions below. Again, this is my wheelhouse. I love this sort of stuff. So we'll see you next time.